So the first thing I wanted to do today was finish for you the proof that the language of reduced words of a Coxeter group is automatic. And remember that the last thing that I mentioned and I haven't proved is this key claim that if generator Si makes W longer, then I want to describe which ones are the small roots that WSI makes negative. And I told you what the answer to this was. They were basically either you take a small root that W makes negative and act on it by Si, or you take the simple root alpha I, and then you just make sure that these roots are actually small. Okay? So remember that the way we use this is that if we have some state of our automaton where we have some roots gamma 1 up to gamma t, and if alpha I was not one of the roots in here, that meant that we would have an edge labeled Si, and that edge would go to the following set. We would take these guys, Si gamma 1 up to Si gamma t. So this is this first part. Then we would add alpha I to this. And then we would just cross off the things that were not small. So we would just cross off some things that were not small and keep only the small ones. So this was the key way in which we built our automaton. The idea being that if these are the negative roots, if these are the small roots that W makes negative, then these are the small roots that WSI makes negative. And so I can think of this as a state for W and this as a state for WSI. And so what I would like to do now is prove this claim for you. Okay? So proof. Well, let's prove the two inclusions, and one of them is pretty easy. Let's say that you have something over here. Okay? So take gamma in the right-hand side. So that means, first of all, that gamma is small, and gamma is either in this category or in this category. Okay? So either gamma is equal to Si times, let's say, delta for delta in this set, or gamma is equal to alpha I. And so in each one of these cases, I have to prove that gamma is on this side. And the way of proving that is I just make sure that WSI sends this gamma to something negative. So I just compute. What is WSI times gamma? Well, in this case, it's W Si delta, which is W delta, right? And delta is made negative by W. So that means that this is negative. So that's correct. And let's do it in the other case. What does WSI do to gamma? Well, this is WSI alpha I. Now, Si alpha I is just minus alpha I, so this is minus W alpha I. And because WSI is bigger than W, that means that W alpha I is positive, which means that this is negative. Okay? So in both cases, WSI makes gamma negative, which is exactly what it means to be in this set. Okay. So that means that one inclusion is pretty straightforward. Now let's prove the other inclusion. Okay. And for the other inclusion, I need to prove a lemma for you, which is a little technical lemma. When we say something is a technical lemma, what we mean is that it's a little lemma that maybe is not so important in the big scheme of things, but it's kind of a little useful thing that will help you finish a proof. And so here's a technical lemma that is going to sound unimportant to you, but you'll see that that's exactly what we need. So here's my technical lemma. Let's say that we take some root which is small, and let's suppose that when we act on it by a generator Si, we get a positive root which is not small. Okay? And let's take some W such that Si makes it longer. Okay? So if I have these conditions, then I can conclude that WSI alpha I is positive. No, sorry. The WSI gamma is positive. Okay? So let's figure out what this means. And once we figure out what this means, you'll see that the proof is pretty simple. So we have some small root, right? So that means that we're here in the root poset. And we have some root gamma, which is small. Now, remember that the small roots form an order ideal. And what that means is that we have this kind of boundary between small roots and not small roots. Okay. Now, Si acts on gamma by either moving it up the root poset or down the root poset. Okay. Now, I'm assuming that, first of all, Si gamma is in phi plus. So that means that when I act on Si, I do stay in the positive roots, which means that I do live in this poset. The question is, do I go up or do I go down? But I know that if I went down, then I would still be small. And by hypothesis, Si gamma is not small. And so what this means is that when I act by Si, I have crossed the boundary onto the not small roots. And we know exactly what that means. That means that this edge must be a long edge, because if it was short, then this would be small, right? So that means that this edge right here is a long edge. Okay? This is a proof, by the way, so I'm just talking, but I'm giving you a proof. You see, my point is that once we understand what this is actually talking about, then we'll see why it's true. So these are the first conditions. Okay. These talk about gamma and Si, and now we're bringing an element W into the picture, and we're just considering any W that is made longer by multiplication by this simple reflection. Okay. And then we're supposed to prove that that W sends this root into something negative. Okay? But remember that we proved this lemma, that when you have a long edge like this, we proved that this guy on top dominates someone. And in fact, we saw exactly who it dominated. We proved that in these conditions, this top root dominates alpha I. So we proved. And You'll have to go back to your notes to remind yourself of this, but we proved that in this condition, in this situation, SI gamma dominates alpha I. Okay? And right. So what does this mean? What does it mean to dominate? Well, it means that if W makes this guy negative, then W is also going to make this guy negative. That's what it means to dominate. Okay? Now, I want to prove that W sends this guy into a positive thing. So let's suppose not. If W SI gamma was negative, then by domination, W alpha I would be negative. Right? But we know that this is not true because WSI is bigger than W. And so these two things contradict each other. Okay. So that's my proof. Just a matter of reminding ourselves of some of the things that we have done. So that's my proof. Now, the question you should always ask yourself when someone gives you a technical lemma like this and it looks totally unjustified is how did I come up with this? And the way that I would come up with this is basically by trying to prove this other direction, getting stuck, and realizing that this is what I need to prove. So I will show you now that this statement is exactly what we need to prove this other inclusion. So let's take something in the left-hand side. Let's call it gamma. Okay. So what do we have? We have, first of all, that gamma is small, right? Second of all, we have that WSI gamma, well, another thing we have is that WSI is bigger than W. Right? This was one of the conditions. And what this means is that WSI gamma is negative. Okay? And so you see, this matches this matches this, and this matches the opposite conclusion to this. Okay? So what this must mean is that because the conclusion of this lemma is false, but these two hypotheses are true, that must mean that this hypothesis is false. So this must mean that SI gamma is not in phi plus minus sigma, right? And so this means one of two things. Either it means that SI gamma is not in phi plus, or it means that it is in phi plus, but it's also in sigma. Okay. Now, in this case, SI gamma is not in phi plus. That means that SI gamma is in phi minus. SI gamma is a negative root. That means gamma was a positive root that was made negative by SI, and that means we know exactly which one it is. Gamma has to be alpha I. Okay? And if gamma is alpha I, then it's in the right-hand side. Because the right-hand side contains alpha I, and alpha I is small. So gamma is in the right-hand side. And if SI gamma is in sigma, then basically I know that SI gamma is in sigma and is made negative by W. So that means that SI gamma is one of the small roots made negative by W. Okay. I want to prove that gamma is in the right-hand side, and I almost have it. Now, if SI gamma is of this form, then I can basically multiply by SI on both sides and get that gamma is in SI times negative. So gamma is in this set right here. And that will mean that gamma is in the right-hand side if I can prove that gamma is small. But why is gamma small? By assumption. Gamma is small, so gamma is in the right-hand side. And that means that if gamma is in the left-hand side, gamma is in the right-hand side, which is the opposite inclusion, and my claim is proved. Okay? So that's the proof of my claim, and if you look at it, you see that I didn't really have any bright ideas here. I just kind of went through the motions and followed the definitions, and this is exactly what I was trying to illustrate to you, that the amazing thing here is the definition of small roots, and once you came up with the right definition, then the proof just follows through. I want to just make a quick comment on this proof of automaticity. So comment on this proof. So here was our first attempt at making an automaton. Represent W by all the roots that W makes negative. Okay, so this was the first. Remember, I started with a warm-up of doing this for the finite groups, and I told you that basically if you represented, so if I represent an element W by just keeping track of all the roots that it makes negative, then this was well behaved. This had the property that this had the property that if you knew where you were standing in the graph and you knew what edge was going out, then you know this, and you can tell exactly where you're going. You can tell what to put here. Okay. This was our first attempt, and we showed that basically this graph worked. The walks in this graph did correspond to reduced words. What graph was it? Do you remember? This was exactly the weak order. The graph was the weak order, which was infinite for W infinite. Okay? And so that means that even though this graph did have the nice properties that we wanted, the trouble was that it was infinite. And so the question that you have to ask then is, how can I do this more economically? How can I represent W in a more economical way so that the number of nodes is not infinite? Okay? And so the second thing you might try then is you might try to represent W by not all the roots that you make negative, but maybe only the simple roots, for example. Because we know the simple roots are finitely many. So that would be the next thing that you could try, by the simple roots. Okay? And then what you would have is a graph that now has finitely many vertices, because delta is finite, and so these are subsets of delta. And so you would get a finite graph. So you would have solved the main difficulty here. Okay? But now the question is this graph well behaved in the way that this one is? In other words, if I give you the simple roots that W makes negative, and I give you the edge that you're going to walk on, can you, just from that information, determine this? And it turns out that you can't. You cannot compute this simply in terms of this set and this SI. You cannot compute it. Okay? So this may have seemed like a good idea, but the problem is you don't know how to walk around this graph, because if you're in a vertex and you walk out of it, then you don't really know where you're going. Okay? So that's not very useful if you want to prove something about this graph. Okay? And so that's why when I started talking to you about small roots, I told you that small roots were really a very remarkable set of roots, because they're just right. I mean, this is, here you're storing too much information about W. You're storing too much information about W, and that means that there's infinitely many nodes. Here you're not storing enough information about W, so that means that you don't know how to walk around this graph, because you're standing here and you don't know where to go. And here you're doing something in between. You're not recording all the roots, but you're recording more than just the simple roots. You're recording the small roots, and this turns out to be just right. This is exactly what you need. And now you know how to go from here to here. And you're finite. That's the beauty of the small roots. They're finite, but they store enough information that you can walk around them. This is just kind of a little philosophical comment on what it is that you had to do to accomplish a proof like this. Okay. Any questions about automaticity? So the next thing I would like to do is something that if you took my Combinatorics class last semester, you know how nice it is to represent things as walks in graphs, because we know a lot about walking in a graph. Okay? In particular, we know a lot about counting in that situation. So let me tell you a little bit about counting walks in graphs. And the corollary to this is that we're going to be able to count reduced words. There's a very nice theory of this. And maybe throughout this whole time, I will apply this theory to the automaton for the Coxeter group we saw last time that I started drawing the automaton for this Coxeter group, and we saw that it kind of got out of hand. And it has something like 16 nodes, which you don't want me to do this live, to deal with a graph with 16 nodes. So let me do a different one. let me consider this group. Okay. And the reason is that I'll show you that you should do it. You should do the automaton, and you'll see that the automaton looks like this. Here's the start vertex. Then it has three edges coming out of this like this. And then there's edges going like this. And there's edges going in the other direction. So if you do the construction that we did for this group, you'll find that the graph that you get is this graph. Okay? And maybe I'll tell you how this graph is labeled. It's labeled A, B, C, this is A. How is it labeled? Like this. Okay. And so we know that reduced words correspond to walks from this start vertex, the black vertex. Okay? And so I'm going to develop a theory of counting walks in a graph, and in particular I'm going to apply it to this guy. Okay? So let's say that G is some digraph. So remember what I told you what this is? It's a directed graph, like this one, where you have vertices, you have edges, and edges are one way. They're directed edges. Okay. So we start with the directed graph, and if U and V are vertices, let me record the number of edges between them. A of UV is the number of edges from U to V. Okay? Now, in this case, this number is 0 or 1. But in other graphs, you might want to allow yourself different edges between the same two vertices. Okay? And now we're going to make a matrix out of these things. Okay? So we make a matrix which is called the adjacency matrix. Okay? So let's do this for this graph. Maybe I'll call this vertex 1, 2, 3, and 4. And so I get a 4 by 4 matrix. And in this 4 by 4 matrix, I say, okay, from 1, I have edges going to 2, 3, and 4. So I get 0, 1, 1, 1. From 2, I have edges going to 3 and 4. From 3 to 2 and 4. From 4 to 2 and 3. Okay? So that's what my adjacency matrix looks like. And now, let me try to count paths in this graph. So I'm going to make a function called P uv of n to be the number of paths that start at U, walk around the graph, and end at V, and they use exactly n edges.
Why is the first column all zeros?
The first column is all zeros because nothing is going into vertex 1. So the orientation is key. Nothing comes into 1. That means that all of these are 0. So if you look at it, basically, we're saying that 1 has edges going to everything except for itself. And 2, 3, and 4 are all connected to each other, except that there's no edge from 2 to 2. There's no edge from 3 to 3. There's no edge from 4 to 4. Okay. So this is the PUV of n is the number of paths. And so what I'm interested in is basically to compute these kinds of numbers. So goal is to compute PUV of n. So for example, I want to know how many paths are there that start at 3, end at 4, and take 1,200 steps. And I want a formula for that because I don't want to do them one by one, right? So how do I do something like this? It turns out that this is something that physicists were really good at. I think they were the first ones to develop this method called the transfer matrix method. So this is something that was developed in statistical mechanics. And this is something that if you do probability and if you work with Markov chains, then you do this all the time. And if you do enumeration in combinatorics, then you end up doing this a lot also. It's a simple observation. Let's say that I want to count the paths from U to V that take n steps. What I'm going to do is I'm going to say, well, let me just look at what was the first step that I took and sum over that. In other words, I'm going to sum over the first vertex that I visited. How many ways are there of doing that? So if W was the first vertex that I visited from U, then how many ways do I have to get from U to W? Well, basically, I only get one step. So that means that it's exactly the number of edges between U and W. Okay? And now I'm sitting at W. I have to get to V, and I wasted one step already. I didn't waste. That wasn't a waste. I already used one step. Okay? And so from W to V, I have to get in n minus 1 steps. Okay? Now, if you look at this I hope looks to you like a matrix multiplication. And the entry UV is summing over W, the entry of UW times the entry of WV. So if I made a matrix, and let me call it P of n, and in this matrix I record for each U and V the number of paths between U and V with n steps, then this matrix by this thing is exactly going to be equal to the adjacency matrix times the same matrix, except it's going to be the matrix for n minus 1 steps. Okay? And what this means basically is that P of n is A times this, which is A times the next one, which is etc. And so what we get is that this matrix P of n is equal to this matrix A to the n times the matrix P of 0. Let's think about the matrix P of 0. How many ways are there to get from U to V in 0 steps? Well, if U happens to be equal to V, that means that when you're at U, you're at V in 0 steps. So you can do it. But if U is not V, then you cannot get from U to V in 0 steps. And so what I just proved is that P of n is simply A to the n, which is a remarkable result. And it says that if I want to count paths, all I have to do is know how to raise my adjacency matrix to the nth power. Okay. So this is the transfer matrix method. And now it turns out that sometimes, I mean, you do this, right? And sometimes you find that the answer that you get for p uv of n is a mess. In fact, generally, you're going to find that it's going to depend on the eigenvalues of A, and it's going to be this big, complicated expression involving the eigenvalues of A. And sometimes, I should say often, a formula for something is better, so leave space here, is better than a formula for this. Okay? Sometimes this is very messy, and a better way of recording this information is by obtaining a formula for this expression. For the series where you fix u and v, and you make a series p u v of n x to the n. So this is what's called the generating function for the sequence p u v of n. Okay. And very often we find that actually a formula for this thing is much more useful than a formula for this thing, because this formula is too ugly and this formula is a lot cleaner. Okay. And so here's a formula for each specific entry, but now I also want to give you a formula. Let's call it a theorem. Theorem. If I want to compute this generating function, then it's very easy. All I have to do is the following: minus 1 to the u plus v times, it's up with determinants today. We need determinants. The denominator is the determinant of I minus xa, and the numerator is the determinant of I minus xa, where you remove row v and column u. So you make a matrix. It's a square matrix because the adjacency matrix is square, remember. And we remove row v, remove column u, we get a square matrix, and we compute its determinant. So this means, actually you can't see red in the video. This means, can't see this either. This means you delete row v, column u. And that's the theorem. So let's see. I think I have time for an example and a proof. What do you want first? I think an example is better first, right? So, and actually I drew my example, so I better give you an example. Otherwise, why did I draw this? Let's see, I can erase all of this. So, for example, now this is for fixed u and v, right? This is for u and v vertices of the graph. This tells us how to count the number of walks from u to v. Now, in this case, we're interested in the walks that start at the start, right? And so let's do this in an example where we start at 1, and let's say we finish at 3. I don't know. So summation from n equals 0 to infinity of p, 1, 3, and x to the n. Okay? So by the theorem, by the transfer matrix method, what we get is minus 1 to the 1 plus 3, so that it's not there. Now let's do the bottom. Determinant of I minus xa. So the identity matrix minus x times this thing. Now you see this thing has nothing in the diagonal, so we're just going to get ones in the diagonal. Minus x times all of these guys, so we get minus x, minus x, minus x, minus x, minus x. We get 0, 0, 0. I don't know about you guys, but I feel relieved that it turns out I don't have to compute a 4 by 4 determinant. Because those have 24 terms. But fortunately, because these guys are all zeros, this is just going to be 1 times this 3 by 3 determinant. Now, what do I put on top? Well, what I have to do is this same determinant, except that I have to remove row 3 and column 1. And so what I get is minus x, minus x, minus x, 1 minus x, minus x, minus x, minus x, 1. And there it is, an explicit formula, and I just have to compute. When you do this, you do it. And I'll tell you what you get. The top turns out to be x times 1 plus x squared. The bottom turns out to be 1 plus x squared, 1 minus 2x. And so what you get is x over 1 minus 2x. Okay? And immediately we got a formula for how to walk around this graph. Okay? Now, our hope is not just to walk in the graph, but to count reduced words, right? So how do I count reduced words? Well, if R sub n is the number of reduced words of length n, then what is R sub n? Well, it's the number of walks from 1 to something. So it's either that I walk from 1 to 2 in n steps, or 1 to 3 in n steps, or 1 to 4 in n steps. I can't walk from 1 to 1 unless n equals 0, right? So this is for n greater than or equal to 1, and for n equals 0, I get R0 is equal to, well, let me leave a little bit of space. But the point is that I can simplify this. Why? Because you see that this graph is perfectly symmetric in 2, 3, and 4. So these three numbers are equal to each other. And I get this. Okay? So that means that the summation of R of n, x to the n bigger than or equal to 0, is just basically this 1 plus 3 times this one. So 1 plus 3 times this one. And there you have it. That's an explicit formula for the generating function of the number of reduced words of length n. Okay? Now, what you hope for sometimes when you do something like this is that, I mean, for example, if I asked you, what's the number of reduced words for n equals 1,000? Well, there's several things you could do. The first thing you could do is just go to Maple or Mathematica or whatever your preferred program is and tell it, just expand this for me and tell me what the coefficient of x to the 1,000 is. That's one way of doing it. But another way of doing it is just to actually compute. It turns out that in this case, this is just a geometric series, right? 1 over 1 minus 2x. In this case, you can find an explicit formula. The formula that you find is this. That means that this number is, this is the number of reduced words. We get a complete explicit answer for the number of reduced words of length n. Okay. Now, I should tell you that once you see the answer so simple, you can imagine that there's a simpler reason for this. And actually, if you now go back and think about what the reduced words are, you're going to find a very easy proof for why the answer is this. Okay? But the other thing I'll tell you is that this is just about the only group where you're going to find an easy answer. So, I mean, it's a little unfortunate that it's the only example that I can draw for you, and then this formula is not very impressive. But just to give you an idea of what these things look like, I think maybe, well, we'll see. What would have happened if I did it for this guy? Well, for this guy, the formula that I obtain looks like this. Okay? It's a nice compact formula. Now, I would like you to compare this with the formula for R sub n. If you multiply this out, you get something that looks like this. Yeah. Where do these square root of 2 and negative square root of 2 come from? They're the roots of this polynomial. Okay. And again, this is one of the simplest examples. So I can at least write these guys out. But if you look at bigger groups, you can get very messy polynomials here. You know that if this polynomial is degree 5 or bigger, you can't even write a formula for me like this. So in general, for Coxeter groups, it's hopeless to write a formula like this explicitly. And this turns out to be much more useful. Okay. So this is why this is a nice accomplishment. And let me write down an explicit corollary. For any Coxeter group, this thing is a rational function. Why is it a rational function? Because it's just a, this is a polynomial in X. And so this is just a combination of rational functions. And this is a very nice theorem because, generally things are not rational functions. Okay? And there are a lot of techniques for computing with rational functions. I guess I don't have time to prove the theorem for you anymore, so I'll prove it next time. Come to the seminars today.
Federico, you were saying root 2 was the root of what polynomial?
Maybe this is not quite right because it should be the. No, it is. I have to admit that I did this kind of in a hurry this morning, and I'm not exactly sure if these are the correct constants. But I am sure that there is a root 2 and a minus root 2 here, because when you factor this, you have to factor the denominator. And this is 1. This is 1 minus square root 2x times 1 plus square root 2x times 1 minus x. And the numbers that appear here are square root 2 minus square root of 2 and 1. And in general, the answer you get here is as ugly as the roots of this denominator, which can get pretty ugly, as you know. I mean, for example, you look at this expression and you can't even tell it's an integer.
Okay. Well,
If you think about it hard enough, you can. But if these roots are really, really ugly, then this is not going to look like an integer to you. But it is, because it's counting something. We just proved it.
but I still don't believe that root 2 is a root to one of those polynomials.
It's a root of the reciprocal polynomial.
Ah.
Because you take 1 over 1 minus square root 2 of x. So what you get is that every power x to the n is in front of a square root. So it's like the roots of the polynomial is the 1 over x.
I asked him not to give it all.
Why 6?
Food, man.
Actually, I asked him to not all the 6, because that's what I'm thinking. You're a slave, man.
Slave to the food?
You're an addict.
Yeah, I am an addict.
Every day, 3 times a day.
Sometimes 4 times a day. Spending all my money on it.
What's the last question you asked it before?
Oh, well, that's cool. I'm gonna go